Hello, welcome to everyone to this Friday talks of the ANH. Today, we'll have the pleasure to have with us the Colombian Geological Survey into the ANH workshop number 27. Today, we'll have the study of a Cretaceous source rock interval into the Magdalena Valley. So those are the talks that we have had on August and we'll be having next week as well. So remember that on August 5th, we have the special guest, Alejandro Mora from Jocol, with the reconstruction of the evolution and infill of the Pliocene to the early Pleistocene to Baragua and the Costa Syncline at the north of San Jacinto Fault Belt. This is a gas-prone basin that is quite important in this transition effect that we'll be having into the exploration and production of oil and gas in Colombia. We had as well last week the understanding and quantifying reservoir heterogeneities using digital outcrop models by Mauricio Vaquero and Germán Bayona from Ares, and as well the sedimentological aspects of the Lizama formation by Medardo Chacon. Today, as mentioned before, with the Colombian Geological Survey, we have a study of the Cretaceous source rock interval into the Magdalena Valley. And next week, we'll have a very special talk that is evaluating carbon storage sites into hydrocarbon-prone basins, a workflow supporting the energy transition initiative. That'll be by Noemi Pernin into the UK by PGS. So during this year and last year, we have presented more than 30 areas, most of them with gas and condensate, and that's the link that will be providing to you via chat for the different talks that we have had during the year. So today we have 3 speakers with us from the Colombian Geological Service. First, we have Dr. Manuel Paez. He's a geologist from the National University of Colombia with a Master in Science in Geology from Berkeley University and a PhD in Geology from the University of Houston. She's an stratigrapher with more than 15 years of experience in research and exploration in the oil and gas industry. As well, we have Nestor Gamba. He's a geologist from the National University of Colombia, and he's got a master's degree in geology from the University of Barcelona with 15 to 18 years of experience in research and exploration into the oil and gas industry. As well, we have Felipe Pastor. He's a geologist from the National University of Colombia and an MSc in geology from the National University of Colombia with 10 years of experience in research and exploration into the oil and gas industry. So to remind to all of you that next week we'll have a special guest, Noemi Pernin from PGS, with a very special talk into the transition initiative. It's called Evaluating Carbon Storage Sites into the Hydrocarbon-Prone Basins, a workflow supporting the energy transition. So I give the stage to the Colombian Geological Service. So thank you.
Okay, thanks, Daniel. Just confirm, can you hear me?
Yes, we can. Yeah, we hear you quite well.
Sure, okay. Then let me just go to PowerPoint and then we will start the presentation.
All right.
Okay, everything looks fine?
We cannot see your screen in this very moment.
Okay.
No, we do.
Okay.
Go ahead. Just.
Good. Okay, thanks. Good morning, everyone. My name is Manuel Paez, and I will be presenting the first part of this presentation. So thanks for being here today. We would like to thank first and foremost the ANH, not only for providing financial support to this project, but also for inviting us to give this presentation. As you probably already realized, we will be presenting the results regarding the evaluation of the Upper Cretaceous rocks in the Middle Magdalena Basin from an unconventional point of view, and more specifically, an evaluation of the Middle Mag Basin, aiming to determine and quantify the potential of the La Luna Formation as a liquid and gas hydrocarbon reservoir. So let me start this presentation by giving you a summary of three specific goals that hopefully we will achieve by the end of this presentation. So the first goal of this presentation is to determine the stratigraphic intervals that show the best potential as a conventional place in the northern part of the Middle Magdalena Basin based on geological information from outcrops and the subsurface. As the second goal, this study aims to describe the structural and stratigraphic features of the northern part of the basin based on subsurface and outcrop data. And finally, we will present a sweet spot proposal based on geologic parameters and volumetric estimations for the unconventional resources of the Salada, Pujamana, and Galembola Renta formations. So as I mentioned in the previous slide, our work has different components. All of them are quite important for the understanding of the La Luna formation at the basin scale. So our first source of information, you can see here, comes from outcrops and is focused on the eastern flank of the Central Cordillera and the western foothills of the Eastern Cordillera of Colombia. In this part, we try to do geologic mapping in areas of interest. We go out to the field, we measure stratigraphic sections, describe rocks at different scales, and then we sample these stratigraphic sections for further analysis, such as DRX, XRF, organic geochemistry, and biostratigraphy. A second and very important component of this work is the seismic information, as well as the core and well data. In this regard, our group has done an effort trying to describe hundreds of kilometers of seismic information, core description of several thousands of feet, and well logs as well. As a third component, and guided by the petrophysicist in our group, we try to determine based on well log information the main components of the rocks, such as total organic carbon, clays, and calcium carbonate. And we try also to determine what will be the more likely behavior of these rocks from the geomechanical point of view. Finally, all this information, at least for this study, was put together in a 3D geochemical model in order to determine the potential of the La Luna formation as a source of hydrocarbons. Something that is very important and is probably a differential compared to previous evaluations is that our group has pioneered the use of big data analysis using the freeware software SDAR, stratigraphic data analysis, that is currently in development, but that allows rapid evaluation of geological information in a robust framework. Now that you know the structure that we follow during this presentation, I will briefly present you the surface data. Then Nestor Gamba will be presenting you the subsurface information, and then Felipe Pastor will present the petrophysics, as well as the basin analysis and the geochemical modeling for the basin. Okay, so these are the three geologic maps. As you can see in the map that is at the center of the figure, this one here, the Upper Cretaceous rocks do not outcrop in the basin. Instead, the Cretaceous rocks are covered by Cenozoic deposits, mainly terrestrial in origin. For this reason, we have to go to the foothills, in this case, the eastern foothill of the Central Cordillera, and to the western foothill of the Eastern Cordillera. Here, I'm showing three different localities that have been mapped and sampled in detail. In these localities, the outcrops are exceptional, despite the fact they are deformed and affected by faults and faults to different degrees. It's also important to highlight that it's only after an initial scouting that we decide what stratigraphic sections will be measured in different areas. So we go, we see the whole area, and we find the best section that is representative of the area and that is not affected by folding and folding. Then we proceed to measure and describe in detail the rocks for a specific area. A good indicator of how intensive the field work has been are the numbers we have for the different areas. So in total, we have nearly 1,200 field stations, 586 square kilometers of maps, and about 2,500 meters of stratigraphic sections measured. This is probably one of the more comprehensive fieldwork studies that have been done in the basin, as we have pretty much been in every locality where there's upper Cretaceous rocks in the central and northern part of the Middle Magdalena Basin. So although I promised you, I will give you just information that was collected from the surface, from outcrops, a more regional picture of the stratigraphic units can be, and that can be useful to determine the sweet spots, can be gained by studying well logs. So we have plenty of information from this from the soft surface, especially well log information. And although we have more restricted information in terms of a spectral gamma ray, the spectral gamma ray is very useful when we are trying to evaluate fine grain and reservoir. So probably you notice here that we have a lot of information in this slide. So I'm not pretending you can read all the information that is contained here. But for your reference, we have the gamma ray to the left. So here, the first column, then we have the depth, then we have the density neutron, then we have the uranium concentrations. And in this column, I want you to focus in this column because that's the uranium-thorium ratios. And the uranium-thorium ratios show striking, or show some important trends in the along the stratigraphic profile. So the first thing you can see is that in the salada, or what we have interpreted as the salada, and we have actually corroborated that interpretation looking at the wells at the cores, the uranium thorium ratios are relatively high, whereas if we go to the Pujamana formation, there is a sharp decrease in the values of the uranium thorium ratio. Then as we enter into the Galembo formation, we have a high value of uranium thorium. And then once we enter into what we have called the La Renta formation, or what was called by Roberto Terraza as the La Renta formation, you see some variable or some changes in the uranium thorium response. So you might be wondering, what does this mean in geological terms, and why is this important for the evaluation of an unconventional play? And the answer lies in the fact that the uranium in the rocks is retained very effectively during periods of anoxia at the water sediment interface. In contrast, thorium is usually found in the structure of heavy minerals and clays. So the interpretation that we are making here is that high uranium thorium ratio indicate preferentially higher rates of organic matter preservation under an anoxic environment, whereas low uranium thorium ratios are indicative of higher input of detrital components and probably associated to this process and oxygenation of the sediment water interface. So that's the important. If these values are higher, we are going to have more preservation of organic matter. That's one of the inferences that we are making. Okay, now we have tried to test lithological correlations and put the information in a temporal framework. So here I'm showing you a chronostratigraphic chart. All these rocks put in a temporal framework, and this is very much a cross section from the southern part of the basin to the northern part of the basin. So we have identified some stratigraphic surfaces that can be useful for correlations and to predict in areas where we don't have information. So that's the importance of this kind of work that we have done for the Laguna formation. Also, speaking of the rocks, let me remind you that our evaluation, at least for now, is only focused on the Upper Cretaceous. So we will frame our discussion on the rocks of the formerly known as the La Luna formation of the Middle Mac. As a side comment, there have been confusion of the lithostratigraphic nomenclature of the basin. So some companies have extended the use of lithostratigraphic formations of the Upper Magdalena Basin, such as the lower and upper Lidita formations. But for the remaining of our presentation, we will follow the lithostratigraphic nomenclature of Terraza for the rocks of the Upper Cretaceous. So I will refer to the rocks under study as the Salada Formation, that is down in here. Then the Pujamana Formation, which is this shale that is shown here in the central part of the chronostratigraphic chart. Following up, we have the Galembo Formation, and then finally we have the La Renta Formation. And I will use that nomenclature instead of using the La Luna Formation. Okay, in the next couple of slides, 5 slides to be more specific, I will show you a couple of rocks in different parts of the basin, both in outcrops and in cores. This summary is based on the detailed description of 2,100 feet of section, and also in the description of 2,200 meters of section in outcrop. As you can see from the cores, probably the map is too small, but you can see some of the cores here in green as green dots. And the stratigraphic sections we have measured that are here highlighted by the red polygons. Our descriptions cover the entire extent of the basin. So we have been in every single part of the basin. Well, at least in the central and northern part. Now I will show you rocks. It's always important to don't forget or not forgetting that the rocks are one of the more important inputs to any model, to any um, geological interpretation. So I will start with something that is not part. Well, that is a separated lithostratigraphic unit. It was raised to the rank of formation by Terraza, and he called it El Salto Formation. It's a unit that is middle Cenomanian in age, and is basically compound of rootstones of oysters, marls with remains of oysters, here denoted by Ma, and medium bedded lenticular connected recrystalline limestones, here denoted by LCL. Basically, our interpretation based on analysis of phases uh, has has led us to interpretation that is a mix of carbonates and siliciclastic. It's an environment where carbonates and siliciclastics are a mixture, and in being more specific, it's a mixed ramp, inner and mid ramp with moderate levels of oxygen. Following up in the vertical, in a stratigraphic sense, from bottom to top, we have what has been called as the Salada Formation, which is lower Turonian, probably middle Turonian in age. Some common lithophases are mudstones and waxstones of forams in thin beds, closely packed with ammonites and inoceramide bivalves. Something that is important is that it's organic rich. It has some thin bentonites, and at the top of the section there is a little change, and we have an alternation of marls and limestones in medium beds. So based on the analysis again of phases, we think that these rocks were deposited in a carbonated ramp with low oxygenation, more specifically in the middle to outer part of the ramp. Then we have the Puhamana Formation. Within this Puhamana Formation, which is mid-Turonian to probably Coniacian in age, we have siliceous mudstones, here denoted by SM, with ammonites and inoceramide bivalves, molly sandstones, such as the ones that we have here, denoted as MS. And then finally, we have in a lower proportion bioclastic limestones, here denoted by BL. Sometimes they can be intraclastic limestones. So it's a predominantly siliciclastic unit, and the environment of deposition is a siliciclastic ramp, specifically the inner to mid ramp, as you can see here from the diagram. Then we enter in another interesting unit from the point of view of the unconventionals, and is the Galembo Formation. Some common lithophases are waxstones of planktonic and finch remains with lamina of paxstones of forams. It's organic rich, as I said before. As you can see in this picture, we have the VE that are basically volcanic ashes, the vitrified volcanic ashes, also known as bentonites. We have metric micritic concretions and silicified limestones that are also organic rich. Based on the analysis of phases, we have a carbonate, or we think that the environment of deposition is a carbonate ramp with low levels of oxygen. With more specifically, it was deposited probably in the transition between the middle ramp to the outer ramp. And this is the last slide that I will present today. So we have what is called now, or what is known now as the La Renta Formation. Is phosphatic rich and is Antonian and companion in age. Some common lithophases, or there is an important changes in the lithophases here. So we have limestones deposited in environments of high energy, such as paxtons of phosphates and fish remains. We also have oosporites, paxtons with intraclass, impure waxtons, and paxtons of benthic and planktonic forams. And something that I want to mention here is this bed here. This bed is an interesting bed because it has a lot of glauconite, or in any case, a green mineral that we still don't know, or we are not sure if it is glauconite or not. But this unit can be correlated to a tres esquinal member in Venezuela and corresponds to a period of reworking of a hard ground, then a marine depositional still stand, and an expansion of an oxygen minimum zone formed by the influence of upwelling currents. So this unit is very important from the sedimentological and stratigraphic point of view because it indicates that there was a reoxygenation of the sediment water interface, probably mediated by upwelling currents. So that's all I have to say for now. So now let's move to the second part of this presentation, where Nestor Gamba will present the results of analyzing or interpreting 2D and 3D seismic information in the basin. So Nestor, please go ahead.
Okay. Good morning. I will show you the results of the subsurface interpretation of the Upper Cretaceous association at the Middle Magdalena Valley Basin. The northern boundary of the study area is located surrounding of the Buturama fields here, and the southern boundary of the study area is located close to Mugrosa field near. In this region is located the most prolific oil fields in the basin, like La Cira here, Casabe, Colorado, Garzas, Llanito, among others. In this zone, nearby Cantagallo and Garzas fields are located the special research project contracts called CEPIS, where it's planned to be drilled the pilot wells Calais and Platero, more or less here. In this map, you can see the data available, which was used for the interpretation, consisting of 15K kilometers of 2D seismic lines, 6 3D seismic surveys, and 69 wells. Red lines represent the seismic profile orientation that I will show you in the 4 next slides. I will start from the northern to southern part of the basin. The stratigraphic column consists of 13 tops, starting from the bottom to top by Pre-Cretaceous in conformity in blue here. Rosa Blanca formation in dark green. La Paja formation in light green. Next, Tablazo, Simití, Salada, Pujamana, La Renta. These are Umir formation. You can see Eocene conformity in orange, and the tertiary succession Esmeraldas here, Mugrosa, and Colorado formation. In this formation that has a north-south orientation, it is illustrated how the Cretaceous succession is consistently higher to the north, and this succession is affected by sparse normal faults. Normal Cretaceous faults that probably were reactivated as a transpressive strike-slip faults during the Upper Cretaceous and early Paleogene, which could explain the generation of white faults. These faults generally do not affect the post-Eocene succession. In the southern part of this profile, nearby Tisquirama well, most of the Paleocene Lizamo formation and the entire Umir formation are preserved. To the north, nearby Buturama and Catalina wells, the preserved Cretaceous succession is minor by erosion due to foreland basin generation during Eocene. The second section includes the Lajas 1, Cristallina 7, and Jumeca 1 well. A system of transpressive fault is observed here, generate positive flower structures in the Cretaceous succession. This feature can be also seen in the third section. This is a third section, where, for example, the Cocuyo 1 well drilled one of these Cretaceous positive flower structure. In this section, you can see how some of these faults affect Paleogene and Neogene successions. This is an evidence of a younger deformation related to uplifting of the Eastern Cordillera. Salida system faults here is present in the eastern zone of this profile, where Nuevo Mundo's incline is located in the hugging wall of this system fault. In the southern easternmost area, the Cretaceous succession is cropping out here. The last profile is located nearby La Salina Infantas High. In this section, you can see that are faults that affect only the Cretaceous successions and other that affect the entire sedimentary succession. In both cases, these faults involves the Precretaceous basement corresponding to the skin structures. Related to the 3D seismic information, the volumes Santa Isabel here, Cristalina, Garzas, Cantagallo, La Rompida, and Aguadas Blancas were interpreted. In addition of the stratigraphic and structural interpretation, an analysis of the maximum curvature attribute was carried out in these volumes. In all 6 volumes used, geometric seismic attributes were calculated in order to enhance structural features not seen in a conventional interpretation. Black arrows, like this or like this, on maximum curvature attribute represent the location of the main faults. For example, this or this or this. Of those that control the structural of the area. In yellow, yellow arrows are interpreted as minor discontinuities, subtle faults, or short wavelength flexures, whose joint interpretation with other attributes and local integration of data would allow us to conclude regarding the relations of these events with fracture zones, for example, here or here. Some of the results of the subsurface interpretation correspond to depth structural maps of the upper Cretaceous succession. And this is like you can see the Salada, Pujamana, and La Renta depth structural maps. In general terms, in the southern part of the area, the faults have a north-south orientation. In the middle region here, there are higher density of transpacific fault with a northeast orientation. In this zone, there is located the deepest part of the basin with a color blue of the contours here or here. Where the units reach more than 16K feet in depth. La Renta formation is restricted in terms of area station due to the rate of erosion is higher in the younger intervals of the Cretaceous successions. White polygons represent erosional truncation of the inconformity acting on the paleoheights, like La Sira, Sogamoso, and Cagüí paleoheights. These maps were input for further 3D geochemical and petroleum system analysis. Felipe told you about the petrophysics and petroleum system analysis of basin. And Felipe, go ahead. Thank you.
Thank you very much, Nestor. Good morning, everybody. So this presentation section will show you the results of petrophysics and petroleum system modeling. The methodology of petrophysics and e-log evaluation corresponds to 3 parts. The first part here is related to the total organic content estimation, which includes the organic porosity calculation here. The second part of the mineral model is the mineral model estimation and determining porosities and permeabilities. And finally, the third part is the estimation of geomechanical properties. We evaluated 40 wells in the basin that drilled the 3 upper Cretaceous source rock of the so-called La Luna formation, the Salada, Pujamana, and Galembo-La Renta formations. In this plate, we present an example of the adjustments to the calculations with the lab data. And in addition, we compiled a database with 1,400 X-ray diffraction analysis and 5,000 pyrolysis analysis from outcrops and data. So here is an example of the different calculations from petrophysics that include total organic content estimation, organic porosity, effective porosity, clay volume, and brittleness index from mineralogy. We plot these calculations in these maps using statistical techniques like kriging or minimal curvature. Also, these maps are input to the petroleum system analysis. Here is the methodology used in petroleum system analysis. First, we compile observations and data from outcrop, seismic, and wells related to several parameters. For example, thickness, stratigraphy, basin geometry, and bottom hole temperatures, amongst others. Second, we compared software simulations from geologic parameters with the data to constrain the simulation. And finally, with the results, it is possible to infer ideas about the petroleum generation, burial history, fluid composition, thermal history, etc. Also, the data allow us to plot and map several parameters for each source rock. For example, we created paleophases, structural and isopac maps, porosity, clay volume, and permeability maps, total organic content, and hydrogen index maps, thermal maturity maps, and overpressure maps. For each source rock, we use at least 12 input maps. In this plate, we present an example of the calibration of physical and geochemical parameters of a 1D simulation. In this case, the red line here, or here, or here, or here, represents the simulation. And the dots here are the lab data or the electric logs. If the simulation is well constrained, the red line should pass near the data and reflect the rock's physical behavior. For example, the density here of rocks usually is higher in depth, or the organic matter quality usually is low if we are going deeper. We modeled 31 wells along the basin here in the map, red dots. Also, we adjust the 3D model simulation with the lab data and the 1D models. As a result, there is a strong correlation between the lab data, the 1D models, and the 3D model with high R-squared values. We made cross-validation of the 3D modeling with the lab data and parameters such as the paleofacies, petrophysics, isopac, structural, and other maps. The 3D model obtained maps consider geologic parameters such as the basin geometry, depth, and compation than maps from well data and contour grading. This plate presents an example of the hydrogen index map from the 3D modeling and the cross-validation with the well data map here and the paleofacies map here. As a result of 3D modeling, this plate has an example of the thermal maturity and the transformation ratio for the Salada Formation. Oil companies drill most of the wells in the basin in high structural areas, and the data reveals no higher transformation ratio values than 90%. So to illustrate this, one of the deeper wells in the basin that reached the Salada Formation, Pico Plata, or Pico Plata 1, shows an 87% of transformation ratio here. Another result of the 3D modeling is the gas-oil ratio estimation, mainly from the retained oil and the retained gas. The gas-oil ratio gives us ideas about the in-solution gases in oil as a drive mechanism for producing liquid hydrocarbons. For instance, attractive areas in the Western Gulf Basin, production in the Eagle Ford Shale, usually have gas-oil ratios higher than 1,000. So each basin and geology have different conditions that control the sweet spot definition. Considering the previous results and the evaluation of many other geology criteria, we propose a sweet spot definition based on 4 main parameters: the retained gas, retained oil, the transformation ratio, the gas-oil ratio, and the porosity. With these criteria, we suggest good parameters that ranks the sweet spot in low, fair, or good. In particular, a good sweet spot area has 5% of porosity or higher values, a transformation ratio higher than 0.5, gas-oil ratios higher than 1,000, retained oil values higher than 5 million barrels, and retained gas values higher than 0.5 billion cubic feet. So the sweet spot maps result from the sum of each map of these parameters. In addition, we consider other parameters applicable to the sweet spot as the natural fracture probability calculated from the curvature prediction and pore pressure analysis. Other parameters, such as the mineralogic brittleness or the thickness, have no implications in the sweet spot definition. And finally, this plate presents the sweet spot maps for the Galén-La Renta Formation, Pujamana Formation, and Salada Formation. The green colors in each map are good. For example, this, or this, or this. The yellow, fair, like this, or this. And the red colors are bad. For example, here, hatch areas or polygons here, like this or this or this, have an additional risk due low pore pressure conditions. Also, these maps compared with the curvature analysis helped predict areas with higher possibilities of occurrence of natural fractures. From another perspective, these sweet spots maps are valuable in conventional oil and gas play definition, including naturally fractured reservoirs or tight sands. And finally, we estimated some values of total resources. For example, the Salada formation of gas total retained after the recovery factor, 1 tera cubic feet, and about oil total retained after the 50% of the recovery factor, 2.32 billion barrels. The Pujamana formation, 0.87 tera cubic feet, and for oil after the recovery factor, 1.32 billion of barrels. The Galembo-La Renta, 0.72 tera cubic feet of gas, and 3.7 billion barrels of oil retained after the recovery factor. The sum of each values give us the total of 309 tera cubic feet of total retained gas after the recovery factor, and 6.71 billion barrels after the recovery factor. So, thank you very much.
Okay, thank you, Felipe. So now, if any of the attendees got any question from the group of the Colombian Geological Service about the Middle Magdalena Valley, you are invited to ask anything you like. There is a question by Elbert Ordóñez. When is going to be published this study, or where we can find it? So from the ANH, we'll say that all of these studies that have been carried out with the Colombian Geological Service will be published soon into the ANH webpage, and there you will find like the final report. If you are interested into any further information, that got to be asked directly via email to the ANH, but shortly, I'm not quite sure about the dates, they will be published. And remember that la convocatoria de MinCiencias, I'm going to say this part in Spanish because it's quite important, will be ending this week. In fact, I think it's today. That convocatoria 9:31 termina hoy a las 3 p.m. Entonces, pues para aquellos grupos de investigación, tanto en la modalidad 1 como en la modalidad 2, como la modalidad 3, que es para semilleros de investigación, y modalidad 1 y modalidad 2, que son para grupos de investigación, tanto en temas inclusive de yacimientos no convencionales en modalidad 1, y en modalidad 3, temas un poco más ambientales como hidrogeología o carbon storage, recuerden que hasta hoy termina la convocatoria, entonces es importante, por favor, que todos aquellos que estén interesados pues puedan subir sus datos o sus propuestas de proyectos. Felipe, I think we got a question for you. So, is there any relationship between OAS and sweep spots?
¿Puedo contestar en español?
Lo ideal es contestar en inglés, por lo que la parte técnica generalmente tenemos gente de otros países, pero como guste, no hay ningún problema.
Okay, no worries. Yes, because if you see the sweet spot maps, usually the areas of the Galembo-La Renta and the Salada formation that have that oceanic anoxic events registered usually are higher compared, for example, with the Pujamana Formation that have environments more from shallow environments, I think. So that's that. I think that could be a relationship between that parameters in the sweet spot definition.
Okay, thank you, Nikan. So is there any other question by the attendees? Okay, so meanwhile, if you got another question, we would like to remind to all of you that next week we have our ANH workshop number 28, where our special guest, Noemi Bernin. Felipe, if you can, maybe you like to read, I think it's a question by Alvaro Montoya again. During Cretaceous, we have 5 OAEs. That means we have the possibility of 5 sweet spots. So what do you think about
it? These maps, we build these maps of sweet spot based on all the thickness of the unit. For example, yes, you mentioned 5 oceanic and oxic events. However, if you see the map is complete for the Salada Formation or the Pujamana Formation or the Galembola Renta Formation, and also considers all the thickness of the units. And also that oceanic and oxic events have impacts in the organic matter content and the organic matter quality that belongs and to the or reflects in the transformation ratio and reflects also in the retained oil and retained gas and also in the water.
Okay, thank you for the answer and for the clarification into the oceanic and oxic events. So we like to, from the ANH, to thank to all of the group of the Colombian Geological Service, to all of the attendees that we had today, and see you next week with this quite interesting talk about a transition initiative into the QI and how to apply geophysics to the carbon storage into reservoir characterization. Thanks again to the group of the Colombian Geological Service and the Virgen Magdalena Valley Studies. So have a nice weekend. Thank you.